I need this on the recording. Okay, hopefully everyone turned in the topic, and if you didn't, please do. I am going to keep accepting these topics until this Friday. There is a late penalty, but it's a small one. But please do turn in your topic. After this Friday, I'm not accepting them anymore. So this is your last chance to get it in. I promise they will be graded by the end of the week as well. But I did want to show you how to find your grades on these and see the feedback, because it's not super obvious. So you have to go to the explain something topic assignment. You should see something like this when it's graded, where you can see this is out of 10. So I got a 7 out of 10. And to see the feedback, if you click on this, you should see a pop-up window. Like so. And if you go over to this speech bubble, if I leave you, so I probably won't leave a whole lot of comments, but if I do need to leave you a comment, that's where it's going to be. So you should check that. Also, if you hit this view rubric button, you will see the rubric that I used, and so that this is where you can tell where you lost points. So like if you didn't turn it in on time, whether you included a project title or not. Exciting. I need to work on that. And so that's just, where you got your points from. So please go ahead and check that once I have it graded. Does that make sense to everyone? Can everyone figure out how to see their, okay. Okay, there was, oh yeah, and I probably talked about to you guys about this last week when you had to do your topic choices, where you might have seen your grade in iLearn just dip sharply. Maybe not, but let me, now that you have grades in for this project, your the iLearn grade, the way it calculates it, I have it set to not accept, to not use any empty grades as part of their overall calculation. And so it was fine before you turned anything in for this project. But now when it calculates your overall grade, it's going to go to the explain something project and say, hey, you have a 10% or a 20% in this project. And it won't pay attention to the fact that just means you haven't turned in more stuff. And so you'll see like a D or an F, because a large chunk of your grade now thinks that you failed horribly. So please don't pay attention to that. If you need to figure out what sort of grade you have, just go to the quiz average column and just figure out what your quiz average is. That'll be correct. You can look at expert TA to figure out what your expert TA grade is. And that's just use those to get a feel for what you're making in this class. Does that make sense? Okay. Okay. Online people. I'm trying. I haven't figured out how to make it work on Canvas yet, frankly. So it'll be exciting next semester too. But yeah, no, that's definitely a thing with iLearn, whether you either freak students out at the beginning of the semester when you include all those empty grades and they're like, why do I start off with an F? Or you freak them out halfway through. It's not perfect either way. That's the spirit. I like the attitude. Okay, there's actually more that I wanted to talk to you about, not just that. But I also wanted to talk to you about the next portion of this, and I'm going to talk a lot more next week when it's actually comes due, but I want you guys to start thinking about it now. So clearly, I am going to tell you to start thinking about the draft. So the next thing that's due are the slide set that you will use to present. And it says draft, but I really want it to be a very complete draft. No like empty spots, no placeholders. I want it to be like if you had to present it that day, you'd be pretty much ready to do that. So this, yeah.
So it's a slideshow, not a paper.
Yes. So good question, William. For the final presentations, I will keep the time slot that we had for the final exam open, and I don't have that in front of me. But the final exam week, we have like a 2 to 3 hour slot, which you can present in person. I will also put up just like a forum where if you prefer, instead of presenting in person, just record a video of your presentation and upload it to the forum, you could do that instead. So you'll have the option of uploading a video to the forum or coming to class during the final exam week and presenting there. Yeah.
So if it's 5 to 8 slides, how are we supposed to hit 5 minutes?
Excellent question. So yes. I don't know if you think so. So generally, I think of a presentation as 1 minute per slide.
But like I like to stat that as in like I use slides so I don't have
to.
I can't do that.
Okay. Well, no. You can. But I don't understand what you're saying.
So like I don't have that much content usually, so I let my slides do all the work. I would just stay still, like I go, so let people read one, and then I'm basically cheating.
Okay. So. A little presentation 101 on slides is actually like an entire field of study on the best way to like present information. I generally like to put images and graphs on slides. So kind of a nice way to do it when you're putting together a presentation is talk through the things you want to talk through. And every step, if you find yourself wishing that you had a picture or a diagram of something, that's what needs to go on the slide. You don't really need to put a lot of text. In fact, text is not your friend because then you end up just reading off the slides and it's not very exciting.
Like, what if I'm a fast starter for them? 5 minutes is hard to hit. Like
5 minutes?
Wouldn't you do like 3 or 4?
Okay, so yeah, actually, I generally under 3 minutes I start taking off points, but 3 to 5 minutes is what I'm looking for. I would appreciate nothing longer than 7. I generally have much more people like trying to push the 7-minute mark than the 3-minute mark, I gotta say. But so I expect between 5 and 8. If I see like a 20-slide presentation, I'm thinking that you're gonna talk for much longer than you think you're gonna.
Wait, so
oh yeah, I'm sorry.
So 3 to 5 minutes or 5 to 8?
3 to 5 minutes is what. So really like 3 to 7 minutes is what's acceptable. I've never taken off points for people talking too long, but I don't always watch your entire presentation if you go over 7 minutes. Under 3 minutes, I do take off points for being somewhat terse. Does that make sense?
Sounds like you're talking exactly.
I assume someone in the comments is saying. Oh wait, wow, I have lots of questions here. Matt's totally cool. You just stay home.
It burns.
You don't need present. Yeah. So you will have a choice of either recording and just uploading the video or coming to class. Different people like different things, whichever works for you. Is there a difference? No, it's so, I am gonna require, even if you do present in class, to go to the forum and like make 2 replies to other people. I'll be very clear about it at the time, but it's the exact same presentation. And really, like, some people get freaked out about making recordings because they spend days trying to make it perfect, so they prefer in person. Some people don't like talking in front of people, so they prefer recordings. So whichever one you want is fine. Any other questions?
So
I see the sections created. There's 4 different sections. We could do that.
So I would probably have like a title slide. I would have one slide for the abstract, because this is just supposed to be like a brief overview. Like, I'm going to talk about this. The introduction, maybe one slide. This kind of helps you add in like how you relate, like what's interesting about this subject. Physical principles might be 2 slides, 1 to 2 slides on that one, depending on how many, you know, if you need 5 graphs, then you need 5 graphs. And then your specific example, again, maybe 2 slides, 1 to 2 slides, depending on what it is you're talking about. Does that kind of, that's how I would split mine up. Yes.
Does the question side have to, without play into the time? So like if I have a slide about questions, am I asking questions without play?
Oh yeah, so like questions that you anticipate or questions you'd like to answer? Yeah, you could definitely put that in. I would put it in probably near the end.
Also, I'm assuming the bulk of my slides are going to be about my examples. That's what I think.
Yeah.
Is that fine?
Yeah, totally fine. Yeah, I do want to see like each one of these things, just because it's kind of helpful to hit each one to fully flesh out your ideas. But if you want to spend a lot of time on one particular thing, again, I have a feeling you're going to talk for 20 minutes. Yes.
No, I'm a fast talker. So like 20 minutes for me is like 5 minutes.
Okay. I believe you.
I am an attention for that. So
I'm just saying, like after 7 minutes, I stop watching. Okay. Any other questions? Okay, cool. I'll definitely make time next week, so you guys can ask as many questions as you need. It's not due until November 4th, but definitely start working on it and start getting all the images and whatnot that you'll need. Okay. Okay, is that everything I need to talk about? I got last week's assignment, hopefully graded by this Friday. Next assignment is due for 2 weeks. We are still in the middle of chapter, what are we on? Chapter 11. We're still doing chapter 11.
It's easy in your drive.
I think I have the due date set on the expert TA, so it'll be due this Friday. That's what it should be. We do have a quiz over the weekend. I haven't quite figured out what that quiz is going to be on, but I'll let you know on Thursday. And I'm hoping to start on chapter 12 today. Everyone pretty happy? Okay. Then, if there aren't any more questions, we can go ahead and work on the physics. Okay, so now I am sharing this screen over here. Okay, maybe I'll try that one again. Share screen. Okay. All right, much better. And let me put up the chat. Okay, so I think we were talking about torque on current carrying loops.
Yeah.
Okay. Had we got to the point where it was really an area? Okay, so torque I the current through the loop, the magnetic field, and yeah, the area. Okay, good, good. Area vector, which I cannot put a vector on this quite yet. Okay, okay. And so let's talk about direction at this point, because I think for this problem, I actually don't remember how I set it up the other day. Did I have my current going clockwise or counterclockwise? Like this?
Yeah.
Okay, excellent. And did I have my magnetic field going to the left or the right? Or up or down? I had it up. Interesting. Choices I made. Okay, and for this one, clearly, we found that there'd be a force on the top coming out and a force on the bottom going in. Right? Oh, right. Oh, yes. Okay, I'm starting to remember. Here we go. And we said that it would spin like that around this axis. Okay, did we move the axis? Did we talk about you can have a different axis? All right, let's do this with a different axis. So if you recall, we calculated the force on each side of this rectangle. We found the force on the left and the right to be 0 because the current was either in the exact same direction or the exact opposite direction of the magnetic field. We found the force at the top to be equal to the current times the length of this wire, which I believe we called B, small lowercase b, times the magnetic field, uppercase B. And that was in the positive z direction. And the force on the bottom had the same magnitude, but was in the opposite direction. And then we calculated the torques by saying we have this axis of rotation. Torque is the lever arm, the radius cross the force, and where the radius goes from the axis of rotation out to where the force is applied. And since that side of the rectangle was A, each of these radii were A over 2. Sound good? I'm doing kind of a quick version here, but so we had the net torque equals the torque on the top plus the torque on the bottom, which was R cross F top. I'm going to say R top cross F top plus R bottom cross F bottom. Did we do a right-hand rule, or did we just say we knew it? We just said we knew it. We probably said that if you push forward on the top and backwards on the bottom, you're really making it spin the same direction. You could also, of course, do a right-hand rule of R cross F, where for the top, R goes up, F goes towards the back of the room, and your thumb goes that way in the positive X direction. X, Y, Z. And then for the bottom, R goes down, F goes into the board, and your thumb still points in that direction. So both of these torques are in the same direction, which is what we were talking about when we spun that box. Okay. So we had a over 2 IBB plus a over 2 IBB, both of these in the positive x direction. We said if you have a over 2 plus a over 2, you really just have a. And then we said a times b is really the area of that loop. A, b times the area. Okay, and this was in the positive x direction. Okay, the next thing I want to look at, just, and this one we're going to do pretty quickly, is what would happen if instead of putting our axis right there in the center, we had put our axis right there. Where we're still spinning, but now let's go through our torques and see what we would get. I'm going to do this one in blue. So for the axis right there, what would the radius for the bottom part be? The distance between the axis rotation and the bottom wire? 0, right? So there wouldn't be any torque on that bottom wire. Okay. What would the radius be on the top wire? A. Okay, so when we calculate the torque in this manner, the bottom would go away, but the top, now the radius would be A, the force would be the same thing, and if you do an R cross F, the direction would be the same as well. And I'm hoping you see that this is the same thing. We have the current times the magnetic field times A times B, the area. So we have IB times that same area. Is that okay? Okay, cool. So I feel that we've satisfied ourselves that this is actually the torque acting on that loop. It's not some weird math thing that we've come up with. But I notice I would really like to get a more general equation for this instead of having to go through each of those steps. And where this more general equation is going to come from is this area vector. Because areas are vectors, right? I hope that earlier this semester when we were doing fluxes, you thoroughly convinced yourself of that. Where if I have a surface area, whoosh, I have the top of the box right here. So if I want to talk about the direction of the area of the top of this box, which way would the area vector of the top of this box be? Perfect, perpendicular to the surface, right? So if I look at the area vector of any loop of wire here, loop, 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 loop. There's my battery. The area vector here would have a magnitude of, the length times the width. And if this is laying flat in my screen, the area vector is pointing out. So my area vector, in this case, points out. And if I put my magnetic field, let's hope it's not pointing in. Oops, actually it's pointing in. Give me a second. Still perpendicular, but this area vector points in because that's the way I've drawn it. If my magnetic field, my magnetic field goes towards the top of the screen there, if I do an A into the screen, cross B to the top of the screen, notice my thumb points in the positive X direction. Yes, perfect, perfect. Which is where we need the torque to point. So instead of writing down I times B times A, what I could write down is for the torque is I A cross B. And that would take into account not only the magnitude of each part there, but it would also take into account the direction of the torque. Is that okay? Okay. Really quick, I do want to talk about how I determined the direction of the area vector. So we knew it had to be perpendicular, so it was coming out of the board or going into the board. The direction of the area vector is actually going to be dictated by the current. Where if you take your right hand and you curl your fingers around in the direction of the current, you'll note that your thumb is pointing into the board. Curl around, into the board. Sound okay? And so if you have a loop of wire carrying a current, the direction of the area vector will be whichever way the current's going. Okay, okay, I got nods there. Everyone pretty happy? Let me ask you a question. This thing was supposed to spin after this happened, right? Where the top was supposed to come out. So like if I had my axis there, is supposed to spin around like that. The top comes out of the page, the bottom goes into the page. What if I looked a few seconds later, this thing had spun around, and this is going to be a terrible drawing, just bear with me on that. So now it's laying flat like that. Does that make sense? Where the current is going around like that. Everyone okay? Okay. Which way is my area vector going now? So I have, I have this box. The current's going around like this. Okay? I like it. It's going up, right? So you curl your fingers around like that, point your thumb goes up. My area vector goes like that, in the same direction as my magnetic field. So my magnetic field and my area vector are parallel. Given that these two things are parallel, what will the cross product A cross B give you? 0, because because cross product takes what's perpendicular between two vectors and multiplies them. But if your two vectors are parallel, there's nothing perpendicular to multiply anymore. So the torque there is 0. Is everyone kind of okay with that? Okay, good. And so what you're going to find, and if you do each component, you'll find a very, very similar thing where each component, like if you go side by side on this rectangle, each component will give you a force, but they'll all be in opposite directions. So they'll all cancel out, and not nicely like they did before and gave us torque. They'll all be outwards. Okay, good. I have that. That looks really nice. A few more things I want to look at here. One is there's this thing called a magnetic moment. And in the next chapter, we'll actually talk about how electrical currents generate magnetic fields. And we're going to look at this problem again and talk about it as this loop of wire being a magnet and just lining up in a magnetic field. But this is where the magnetic field, this is kind of where it's going to start, where we're going to call something a magnetic dipole moment, which is almost a magnetic field, where the magnetic dipole moment is kind of the magnetism of a loop of wire. It's called a moment because anytime your current changes, your magnetic moment also changes. So this isn't an inherent property of a loop of wire. It's a property when you put a current through a loop of wire. Kind of like rotational inertia, we call that moment of inertia because it entirely depended on how the thing was moving. And so if you were going to look at, say, this loop of wire here, let me draw it sideways because that'll be easier for me. So if I had a loop of wire like this where my current is going around like that, my magnetic moment and also area vector would be coming out like that. Make sense? Where you could pretend that this was a magnet with a north side over there and a south side over there. And it would have, magnetic fields like that. And if you didn't know it was a loop of wire, you really would not be able to tell the difference between the two. Okay, and everyone seems pretty happy with that. Let me ask you a question from here. I've been talking about a loop of wire. What if I had two loops of wire? What would happen to the torque here? If I just had two loops of wire on top of each other, like one loop, two loop. What do you think?
Would it double?
It would double. You'd be right about that. Because for every wire there, instead of one wire carrying this current, you'd have two wires carrying the current. Same current, same lengths and everything, so you'd have twice as much force. And so two loops of wire just gives you twice as much current. Three loops gives you 3 times. And so you can say the magnetic moment of a coil is not just current times area, but it is the number of loops times the current times the area. Number of loops. Sound okay? And the torque then becomes a really reasonable magnetic moment of the coil across the magnetic field. Okay. There's one more thing I want to look at this here, and then we'll do a problem. And that is the energy in this system, in the loop B-filled system. Because clearly, if you start here and it's about to start turning, so if I can drop a loop of wire into this magnetic field and it will start spinning, clearly it had some potential energy that could become the kinetic energy of this thing spinning. And so that's that's what we'd like to look at, where the potential energy of that loop B field system would be equal to the amount of work that the magnetic field would do on the loop of wire. Since we're talking about rotational stuff spinning, it's not force dot displacement in this case, it's torque dot angular displacement. And so I don't know if you'll remember this. I'm not even sure I did this last semester. It's such a small thing in mechanics. Where if you want to calculate rotational work instead of force dot displacement, so something moving a line, you say, okay, there's a rotational force and it's causing a rotational displacement. Where we are going to go ahead and start this at some angle, in particular 90 degrees, because if your area vector and your magnetic field aren't perpendicular, you're going to be in trouble. There's no energy in that. So if I need to start here, if I want to see anything. Does that make sense? I hope so. Okay. Okay, for the torque, we will throw in this equation. So I have 90 degrees and theta F. That's mu cross B. And that will be dotted with d theta. If we do something in the mu cross B, if we take the cross product of mu and B, we end up with mu, the magnetic moment, B, the magnetic field, and the sine of the angle between them. Okay, and we are going to assume that the direction of this torque is in the same direction as the rotation. So when we started here, we see this torque, it's going to cause this thing to spin. So the direction of the torque, the direction it's being spun in, is the same as the direction of its angular displacement. Okay. Okay. Let's put in mu was NIA, where N was the number of loops, the current, and the area. I have B, I have the sine of theta, d theta. For this problem here, we would expect the number of loops of the wire to change or to be constant. I'm hoping constant because I wanted to expect this thing to grow loops of wire. Okay, so N's a constant. How about the currents? I have a battery hooked up here. I have whatever circuit it's hooked up to. Would we expect the current to be constant? Okay. Area of the loop? Constant. How about the magnetic fields? Constant. And while we certainly could talk about the magnetic, any of these things changing, like in a case-by-case basis, we wouldn't expect them to change with respect to theta. So as it rotates, we wouldn't expect that to change anything. Okie dokie. What is the integral of sine?
The negative cosine?
It's, no, I think you're right the first time, negative cosine. So we have negative NIB 90 to some later theta times the cosine of theta. Okay. Plugging in our limits, we have some final theta, and then we have the cosine of 90. And what is the cosine of 90? 0. Okay. So now I have negative, and I have all of this stuff here, and I have a cosine of theta. And because we have been doing cross products and dot products, I see that cosine of theta, and I want to say there's a dot product here. So I want to say something about dot products because I see this cosine. And then I notice that, okay, that is the magnetic moment. There's the magnetic field. This cosine, that angle is actually the angle between the magnetic field and the magnetic moment. So we can write this as the magnetic moment dotted with the magnetic field. And that'll be how much magnetic potential energy there is in the system for this object to spin. Everyone happy-ish? Okay, cool. All right, given all of that, so that's kind of the last thing I wanted to look at there. Yes.
So what happened to the cosine?
Oh, it got sucked into this dot product. Because yeah, that's mu times b times the cosine of the angle between them. Okay, but if that's okay-ish, we'll probably come back to that in 2 weeks. I just wanted to make sure we had it. I would like to do some homework problems. I'd like to do number 9. By the way, if there's any homework problems from this chapter that you guys want to do, let me know, because I will be happy to stick that at the end here. But number 9, I definitely like. So for this one, we have a circular coil with n turns. And generally when you say like number of loops, you just call those turns. So I have this coil that's like coiled up, and I'm not even going to add those because that's going to mess up my picture. Okay, there's a current going like that, and there's a magnetic field going like this, where they tell us the current, they tell us the radius of this coil, and they tell us that the magnetic field is 0.6 Tesla. Okay, and we're gonna figure out things about this. So first, which way is the area vector for this loop? It's up. Because yeah, if you curl your fingers around the direction that current's going, you should get towards the ceiling. Okay, so we have an area vector going in the positive y direction. What does that tell you about the direction of the magnetic moment? Also be up. So your magnetic moment has the same direction as your area vector. That's why you could treat it like a magnet, kind of. Okay, so magnetic moment's going that way too. Okay, so for part A, when they ask us for the magnetic dipole moment in terms of N, I, and R, one, we know it's in the y hat direction, but also let's use this equation to figure that out. Okay, so I have number of loops, I, and the area. Now, N and I, totally happy with, but we don't have the area. We have the radius of a circle. So what should we put in for this area? Pi r squared. So this will be N I pi r squared in the y hat direction. Everyone pretty happy with that? Okay, okay. For part B, you're gonna just plug in numbers. And for part C, you're gonna say, tell it it's upward because it's in the y hat direction. And now let's look at this torque. So down for D, we want the torque. Okay, torque. Okay, in Newton meters. Okay, let's look at this. Which way do you expect it to spin? And one thing you might think is you're looking for this magnetic moment to line up with the external B field, right? So if our magnetic moment is in the y direction and our B field is in the x direction, like that, which is clockwise. Exactly right. Make sense? Okay. So we are expecting to see a spin like that. Okay, good. Now let's figure out how to calculate that. To calculate that, we're going to go back and we're going to say, look, I have a nice torque. So I expect the torque to be I A cross B. Okay. This will be I A B times the sine of theta in the direction you guys have already told me. So we've dealt with the direction. Theta is the angle between the area vector and the magnetic field. For this picture where we're starting out, what is that angle between the area vector and the magnetic field? 90. I like 90. And what is the sine of 90? 1. Solid. Okay, so we're down to a really straightforward. No, there should be an N here. I'm sorry. Because we have N terms. My bad on that. We have NIAB. And since this problem asks specifically for an equation in terms of the magnetic moment and the magnetic field, do we have the magnetic moment in here? Yeah, so this is just the magnetic moment, right? So we can just say mu times B here. Is that okay? Okay, cool. And then you can certainly plug in numbers and do your work there. If I were going to ask you in terms of X, Y, and Z, do I like the clockwise? I might not like the clock. Yeah, clockwise. That's clockwise. Yeah, okay. In terms of X, Y, and Z, if this thing is spinning clockwise, what direction is that in terms of X, Y, and Z?
Just like positive X?
It's the one direction it's not going to be moving in. In the Z direction, you got it. And it'll be the negative Z because if you curl your fingers around in the direction it's spinning, so it's spinning like a clock, it's going into the board, right? Does that make sense? And this is like we did angular velocity last semester, where you wanted to know that third direction. You curled your finger in the direction it was spinning and pointed your thumb. Make sense? Okay, hopefully it did. So this torque is in the negative Z direction, or you could call that into the board if you wanted. You're fine. Okay. Everyone kind of okay there? And if you are kind of okay there, are there any other problems that you guys are interested in looking at? Because if not, we'll just move on. Okay. Okay, cool. Then that wraps up chapter 11. Yeah, that wraps up chapter 11. I'll have this homework due on Friday, so you can look at it until then, and we can start talking about chapter 12. I'm happy with that. Okay, chapter 12. It's a math-heavy chapter. Sources of magnetic fields. Okay, so things to talk about here. We've talked about one source of magnetic fields, right? In particular, we've talked about magnets, where we said every little particle that makes up matter, like electrons, protons, even you can break it down to quarks, they all have like some magnetic properties. And so a permanent magnet is a material where all the little magnetic properties of the particles line up, so you have an overall strong magnetic field in one direction. However, there are other ways to make magnetic fields. And I don't think you're going to be too surprised that you can make them by running a current through a wire. So just kind of like these loops of wires had magnetic moments, we're going to be able to specify very closely, if I have a current moving through a wire, what sort of magnetic field is that going to produce? Have you guys ever made an electromagnet, by the way? No, okay, I got one nod. You got 2 in class, in lab this week, by the way. How did you make it?
I did it in lab today.
You did it in lab today. Excellent. I'm so glad. How did you do it in lab today?
There was 2 different ones. One was just a wire that we ran electricity through.
Okay.
Run through, and that gave it a magnetic field. And then there was another one where we wrapped the wire around iron.
I liked it.
Did that, and it was a stronger magnet.
Indeed, yeah. So that second one, you wrapped a loop of wire, right? So again, you're back to these loops. They make really good magnetic fields. And when you put that iron core in it, iron is a really good paramagnet, so it picks up magnetic fields really easily. And so with that extra influence, you're able to produce a stronger magnetic field. And so that's really what this chapter is about, is if you run a current through a wire, what sort of magnetic field should you expect? And we're going to do it the hard way first, and then we're going to do it the easy way. So let's start with the biot-savart law. Which is very much like a hit it with a hammer sort of method. It's not, it'll always work, but it's not pleasant. So if I have a wire like this, and if I put a current through this wire, one thing that you will see is that it will make a magnetic field in a loop that's kind of perpendicular to the current, right? So, oops, my arrow's in the wrong direction. It will make a magnetic field in a loop, but this B field should be pointing like this. So if you point your thumb in the direction of the current, curl your fingers around, you'll get this loop of magnetic field that's in the directions that your fingers are curling. Sound okay? We'll do a lot of those as we go through. But the couple things to notice is it's not a loop, so you don't see like this sort of thing. It's very radial sort of loop, so you expect it to be, if you go out along the radius, like if you start at the wire and you go out along the radius, you expect the magnetic field to be the same in all directions. Does that make sense? Okay, yeah, so you don't expect your magnetic field to be tilted like that. Would you expect your magnetic field to be stronger closer to the wire or further away? Closer, okay. So we expect these magnetic fields to have an R dependence, where R is going to start at the wire and go out to wherever we're looking at. So as R gets bigger, B gets smaller. What about current? If we have a larger current, do we expect a larger or smaller magnetic field? Larger. Okay, so we expect whatever magnetic field we get to be directly proportional to the current. Okay, so the biot-savart law says, I'm going to write it in differential form first. If I have some wire and I take a small chunk of this wire, length ds, like that, and I look at some point P out here, some radius R from the wire, such that the angle between ds and R is theta. The amount of magnetic field produced by that little chunk of wire, some distance R away, equals mu naught over 4 pi times the current times ds cross R, and that's R hat, over the magnitude of R squared. Okay, there's a lot here. Let's break this down. First, mu naught over 4 pi, constant. They just talk, we're gonna discuss mu naught. Have we discussed mu naught yet? I don't remember. Okay, I'm gonna discuss it probably on Thursday. It's very similar to epsilon naught, the permittivity of free space, where mu naught is the permeability of free space. It's how easy or hard it is to get a magnetic field in somewhere. Over 4 pi, again, we got some constants running around. Okay, we have the current in here because, of course, if the current increases, we expect our magnetic field to increase. I have a 1 over R squared dependence. So as we get further away, our magnetic field, our R gets larger and our magnetic field gets smaller. I can, I'm going to move on. No, I'm not going to move on. So if you think about what's happening, you're moving out as a circle, right? And so as you're moving out, you can think of this same magnetic, let's call it energy for the moment, magnetic field or magnetic energy getting spread out over this area. And since areas go as distance squared, we're spreading out this thing over a distance squared. Is that okay? Okay, yeah. So r 1 over r squared dependence. Then we have this ds cross r. Now, the r hat, that's a unit vector, magnitude of 1. So it's not going to make this thing bigger or smaller. It's just telling us about direction. Our ds, very small chunk here. So it's not something that's going to get bigger or smaller. Again, it's really just there to tell us the direction. So this ds cross r is really just about direction. Where if you take the ds, so the way I've drawn this ds, you have, it's going in the x direction, forward direction. You cross it with r, ds, r is kind of coming out. The magnetic field at that point we should see is going down. Okay, so we expect our magnetic field at this point to be going down. Now, if we do that right-hand rule I just talked about, put your thumb in the direction of the current, curl your fingers around. When you're out in front of the wire, you expect the current, the magnetic field to be going down, right? And so that's what this is telling you. Like at this point, we expect the field to be going down. If you had some point behind the wire, over here, where our r would be going in the opposite direction, ds cross r, you'd expect that to go up, right? And that's because you expect this loop of magnetic field on the opposite side of the wire to be going in the opposite direction. Okay, cool. So, okay, so basically we have constants. We have the r dependence there, and we have this magnitude factor where if it gets larger, you expect more field. And then this thing is really just about direction. Okay. Clearly, we won't just want one little bit of the magnetic field, we'll want the entire thing. So what we'll do then is if we want to add up all our little bits of the magnetic field, we'll have to add up both sides of this equation. And so we'll end up with the total magnetic field equals the integral of this whole thing, mu naught 4 pi I ds cross r hat, r squared. And so what are we integrating with respect to here? What are you tempted to say that we're integrating with respect to? R is not bad. Not what we're looking for, but not bad. Say again? S. Yeah, S. Because it's got a D in front of it, right? R is not bad, by the way, because it is something that we can definitely think about changing. But what we're going to do is we're going to say, hey, I really just want to know about the magnetic field right at this point. And so we'll get our magnetic field in terms of R. But we're going to think about how each little bit of wire is going to contribute to the magnetic field at that point. Okay, that means that mu naught, I, and 4 pi are all going to be constants. And then we're going to integrate ds cross r hat over r squared over whatever portion or all of the wire that we care about. So we're going to keep on adding up DS's until we get to the total length of the wire. Notice that we're going to keep R inside our integral because we don't know if it's going to be constant. In fact, given that as we change our DS's, even in this picture, our R changes. It's a variable. Just not the one we're integrating. Okay, everyone looks okay. How much time do I have? Let me define what we're going to do next time. We have a long problem coming up here. Okay, so from a long straight wire. Okay. So on Thursday, what we're going to do is we're going to find equations of magnetic fields due to different configurations of wire. We're going to start with what's actually going to be the most difficult one, but it's the most simplest situation. I just have one long straight wire, and we're going to figure out the magnetic field of that. We're also going to do, of course, like a loop. We'll do a solenoid. We'll do the loop using this, and then we'll learn another method, and we'll do a solenoid, and we'll do a toroid too, probably. So basically, we're just saying, okay, I can put wires in all sorts of shapes. What sort of fields would I expect? So I'm probably going to repeat myself a lot. But if I have, but starting with this long straight wire, I'm going to have a current. And what we're going to want to end up with is some equation with a magnetic field. What sort of things do you think that we want to have in this equation at the end of the day? And I'll give you a gimme. I want to have current in this equation. What else might you want to have?
The R.
Yeah, I might want to have some because I'm going to ask you, what if you have a point here, or what if you have a point there? So we're going to want to see some sort of R dependence, where it'll be we'll see like a 1 over R, and I forget if it's squared or not, but we'll definitely see an inverse dependence on that. Probably, of course, going to see some constants, some mu naught, some 4 pi's running around. That's not going to change. Some pi's. Okay. Okay, so I think I'm going to stop here. When we pick up next time, we will pick out a point P. We'll write down for that point P what R is, what ds is, what I is, and then we'll try to do this integral. Okay. Online people, are you guys okay? Okay. Don't forget, if you need to turn in the topic, the outline thing, that you get it turned in, because I stop accepting those on Friday. Okay, see you Thursday, everyone.
Yeah.